All right, we're going to finish Chapter 1 today. We're actually going to stop with Chapter 1. We may have a little time, but we'll just work on your worksheets instead of moving on to Chapter 4. Today is a really important class because we're learning to convert from one set of units to another set of units. And we'll continue using this, but we'll be using different units such as grams and moles and that kind of thing later. So it's important that you understand today, for really the whole rest of the semester, we'll be converting from one unit to another. Okay, how's the lighting? You want me to turn one off? So, okay. All right, so in chemistry we use the SI, or the International System of Units, for measurement. However, some of these are not as familiar to you guys, and that's because the United States is the only country in the world that doesn't use the SI units of measurement. Okay, so everybody else does, but in chemistry we do, because we communicate with people from all over. We want to use that SI. I guess we just like to be different. For length, we use the meter, so there's the symbol that's given for meter. For mass, the kilogram, okay, kg. Okay, time in seconds. And then for volume, the cubic meter. Temperature will be in Kelvin. So some of you may not have heard of Kelvin before. Most of you have, obviously, you've used Fahrenheit, but you've also seen Celsius, I'm sure. But we'll also learn to convert to Kelvin. And then for amount, we use the mole. Okay, we're not going to get to this today, but we will very shortly. You'll get very familiar with using the mole. I'm just quickly going to show these. These are in your book. You don't really have to memorize these, but these are just nice prefixes to kind of start to get familiar with whenever you see the prefix mega. So whether it's mega meters or whatever it might be, you want to think of 10 to the 6 or a million. Okay, one that's common that I always think of is kilo, is like I think of 1,000. So 10 to the 3rd. And we can keep going with these. So you've heard of centimeter or decimeter, and these are just kind of, you can start to label or think about the names, the prefixes that go along with, for instance, milli. So everybody heard of a millimeter? Okay. And so the multiplier would be 10 to the negative 3. So there's 1,000 millimeters in a meter. Okay, so you just kind of can start to put these together. And then we can go further. A lot of these we won't use a whole lot. So really small numbers, so nano and pico. Okay, so what we're going to do, we're going to go over real quick mass, the difference between mass and weight. These are actually two different terms, so we're going to talk about that. And then we're going to start to learn to convert. So a lot of you, even just in everyday life, you've probably converted from inches to feet or minutes to seconds, and use that just in your own, or just done it in your mind while you were calculating how many miles it was going to be till you got to a certain destination or whatever that may be. So we're going to be doing that today, and then kind of get to where you've got maybe a 5-step calculation. I think will be the maximum that we'll do today. But before we get there, there is a difference between mass and weight. However, you hear professors and whoever it might be interchange these all the time. I have to watch what I say because I'm likely to do it as well. Okay, mass is the measure of the quantity of matter in a body, and this is measured by a balance. Okay, you'll learn to use the balances today, and the balance kind of counteracts for the gravity. Okay, and so the mass of an object is the same, whether you're here on Earth, whether you're on the moon, whether you're anywhere in the universe, it's the same. Okay, that's the mass of an object. It should be the same no matter where you are. However, the weight is the measure of the gravitational attraction for a body. So when you get on a scale in the morning, you're weighing yourself. Okay, it's accounting for the gravity or that gravitational attraction. Okay, and so in the lab, when you use a balance, this is the mass. So you would correctly say, I am going to go determine the mass of blank on the balance. Okay, but when you use a scale in the morning, you wouldn't say, my mass is 100 pounds or whatever. You would say, I weigh 100 pounds. Okay, so here's some common conversion factors. Some of these, which you already know, 2.54 centimeters in an inch, be a very common one. And you have all of these. I've tried to put all the ones that, I think I handed my sheet out to, meant to keep one for myself. But I tried to put all the ones that are very common that I will use. I will give you this list on your exam. You don't have to memorize all the conversion factors. The thing you have to do is be able to know how to use that list and use the conversion factors. So there's some in your book as well as the handout from Blackboard, which is what just circulated around. Okay, so we're going to use what's called the unit factor method, or it's also known as dimensional analysis. Okay, a lot of people, when they see that in your syllabus, dimensional analysis sounds kind of scary, but it's really not. It's just converting from one unit to another. Okay, and so what we're going to use is we're going to use conversion factors, and these are the numbers that are listed and the units that are listed on your sheet or in the table. And basically, you're going to write these out as, so if there's 1 foot in 12 inches, okay, we can either write that as there's 1 foot per 12 inches, or we can flip it over. So we could say there's 12 inches in 1 foot. Okay, these are considered to be conversion factors that we write out. Okay, one thing to remember, it's been a while since Wednesday, but when we use numbers from your conversion factor sheet, these are exact numbers. Okay, they don't play a part in determining the number of significant digits that you should end with in your answer. Okay, so I'll kind of show that and clarify that here in a second. Okay, so let's just do a simple one really quick, one that most of you have probably already done, like I've said. And we're going to convert from 7 feet to inches. So we need to go from feet to inches. Okay, you'll hear me say this a lot. The first thing that I always do when I'm given any word problem is I write out what I know. Okay, so the first thing that we know that we have 7 feet. Okay, and we are trying to find inches. Okay. The next thing I go ahead and do is I go ahead and draw me multiplication sign and like so. Okay. I set it up this way with feet here in the denominator because my units have to cancel. Okay, what I'm trying to move away from needs to cancel, and whatever you're trying to find needs to be left on top without it canceled out. Okay, and so then I plug in. So we look at our conversion factor sheet, or we see up here, so I already have it written. These are our 2 conversion factors. Okay, so we have 1 foot per 12 inches, or 12 inches per 1 foot. Okay, and so then we have to choose which way do we want to plug this in. Okay, so do you guys think we're going to pick the first one, or are we going to pick the second? Second, because feet is in the denominator. Okay, and so we're going to plug in our 12 inches in 1 foot. Our units cancel. Okay, so we end up with 7.0 times 12. Okay, and so before I write the answer, how many significant digits are we going to have in the final answer? 2. Okay, why? Exactly. Okay, did the fact that we have 2 and 12, does that play a part at all in determining? Exactly. So it's that initial number. A lot of times, whatever number you're given in the problem is going to be how many significant digits, or how many ever significant digits it has will be what you have in your final answer. Okay, so we end up with 84. Okay, Okay, we don't just end with 84 inches. Okay, you have to be sure that you also include the unit. What it's doing to me here. Okay, so this is just kind of a stepwise process. Some of you may want to go through this and think through this every time, but since we're just starting, I want to go ahead and just walk through these steps. So if we put it out just simple, plain, put it into steps here. We are going to state the given and needed quantities, which is what we just did for the previous problem. Okay. Then we have to write a plan. So we've got to get from point A to point B. Okay, there may be one step in between, there may be two, three, just depends on what we're converting to. Okay, and then we're going to state what conversion factors we need. Okay, so you're going to look at your conversion sheet and you're going to try to figure out your plan, and then you're going to write out those conversion factors. Okay, and then you have to set up the problem so that the units will cancel until you hit your final answer. Okay, so another simple one here. How many minutes are in 2.5 hours? Okay, easy one. You guys, I'm sure, have done this one before. All right, so we need to find minutes. So our plan is to go from hours to minutes. Okay. All right, so our conversion factors, this is not on your list because I assume that everyone knows this. Okay, 60 minutes in 1 hour or 1 hour in 60 minutes. Okay, and so which one we use depends on which way we want our units to cancel, or that our units will cancel. Okay, so we write out what we know. So I've got that written here. We have 2.5 hours. Okay, and so then I go ahead and I place my hour unit in the denominator because I know that my units have to cancel. Okay. And we're going to use this first conversion factor. So we put 60 minutes per 1 hour, and then we multiply and we get 150 minutes and two significant figures. Okay, remember that when we do not have a decimal place, this 0 is not significant. Okay, so we have 2. The 1 and the 5 are the two significant digits. Okay, any questions? Okay, so this one, jump kind of easy one to one that's quite a bit more difficult. I'll go ahead and say to you that there's not always just one way to solve for these. Okay, this is actually the longest way, so starting with yards, going to feet. But if you look at your conversion factor sheet, you can actually simplify this. You could go straight from yards to inches, or you can use, there's different ways that you can go about this. Okay, but if we were to walk through, so I'm going to walk through this. Okay, so we need to go from yards to millimeters. Okay, and so we've got to fill in the plan in between there. Okay, so this is where you have to know how to use your conversion factor sheet. You don't have to memorize it, okay, but you have to know how to use it. Okay, and the way that I chose was the stepwise approach that, not a shortcut way here, and start with yards and go to feet. So I would look at my conversion factors list, and I would say there's 3 feet in 1 yard, or in 1 yard, there's 3 feet. Okay, once I found feet, I would look for a common relationship between feet and getting to millimeters. Okay, so you have to know you're looking basically for equalities. You're looking for common relationships that will get you from one place to another. Okay, and so then I would continue on. So if I'm at feet, and now I'm going to a smaller unit. I've got to go all the way to millimeters. Okay, so then I would start thinking, okay, what's smaller than an inch? Okay, it would be a centimeter. Okay, so then I can go from inches to centimeters. So I'd write out, there's 12 inches. So I'd write out all of my conversion factors here. Okay. 2.54 centimeters and 1 inch. Hopefully you're getting the idea here. Or you can have 1 inch and 2.54 centimeters. Okay, so you can write out all your conversion factors. As you get better and better at this, some of you may already be good at this, you don't have to sit there and write out every conversion factor. You kind of see how it works. You either flip it over or plug it in. Either way, you just plug it in so that your units will cancel. Okay, but if you want to start out this way, you can. Okay, so we start out with 9.32 yards. That's what we're given. So that's what's stated. So we write this out. We know that we're going to have yards in the denominator. Okay, and so we're going to cancel the yards. Okay, and we have feet that's left over, but we're not looking for feet. We're trying to find millimeters. So here we've got to continue on. Okay, so the next thing I did is I went from feet to inches. Okay, so we can cancel our feet. And now we have inches in the numerator. So if we were asked for inches, then we would stop here. Okay, but we're not, so we're going to keep going. Okay, in 1 inch, there's 2.54 centimeters. Okay, and if you look at your list, you'll see that in 1 centimeter, there's 10 millimeters. Okay, and then you multiply everything on top. So you would take 9.32 times 3 times 12 times 2.54 times 10. And then here it would be divided just by 1, because you have 1 times 1 times 1 times 1. Yes.
On the answer for that, the previous one, like this need to be written out as 8.52 times 10 to the third, like just say 8,520.
That's fine. When you start getting into larger numbers, that's kind of borderline. That would be fine. Yeah, as long as you show the right significant digits. All right. I want you guys to do this one. So this time we're going to be dealing with volume. So you'll notice that so previously we were looking at length. So we looked at the relationships that we had to get to millimeters. Okay, now we're going to be in the volume category. So on your conversion factor sheet, you would look for under volume. Okay, we're going to go from milliliters to gallons. Were there any of the conversion factor sheets left over by chance? Okay. Can you share? Okay, so first you've got to devise a plan. So if you look at your conversion factor sheet, okay, so you can write out your plan like we showed, kind of the stepwise process, or you can just kind of think through it. I don't require you to show me your work as far as getting your plan together, but I do require you to show me your work as far as for showing me how you converted from one unit to the other. Okay, so we look here. We've got to get from milliliters to gallons. So we write out what we know. So we're always going to have milliliters on top, and we're going to have that same unit down in the denominator so that our units can cancel. Okay. So the first step that I chose is to go from milliliters to liters. That was just kind of an obvious step in the right direction. We're going from a smaller volume to a larger one, if you want to think of it that way. So we're going to get to liters. Okay. And then if you look at your conversion sheet, we want to get to gallons. So I think on the sheet all I see is that we have 1 gallon equal to 4 quarts. Okay, so we know we're going to have to get to quarts at some point. All right, so we can get there by going from liters to quarts. Okay, and so in 1 liter, there's 1.06 quarts. Okay. And most of you may already know that there's 4 quarts in a gallon. So now we can cancel our quarts. We're left with gallons as our units on top, not canceled out. Okay, and so then we multiply 627 times 1 times 1.06 times 1 divided by 1,000 times 1 times 4. Okay, so when you do the math here, you should get about 0.166 gallons. Okay, did everybody get that? Good. I'm not going to do a whole lot of three-dimensional units, but I do just want to show one just to be sure that we have covered this. But if we look at volume, it's a three-dimensional unit, and so we have to use cubic terms. Okay, you still would use your conversion factor sheet the same way. You just have, yes?
The last one, after you multiply 627 by 1.06, what number did you divide by? Divide by 1,000.
Yes, 1,000 times 4, so 4,000.
Why do you
Which part? The
dividing it by 1,000 times 4?
Yeah, you have to multiply everything in the numerator, multiply everything in the denominator, and then divide the two into each other. Okay. Okay, so if we have 2.61 feet cubed, and we want to convert to centimeters cubed, we would do the same thing. We would convert from feet to inches, and then from inches to centimeters. Okay, so kind of the obvious route to take. Okay, so our feet would cancel, but the only difference here is that we have feet cubed. Okay, so we're going to have to cube this number here. Then we would go from inches to centimeters, which we would also have to cube. One of the most common mistakes is students will cube the first number. Okay, you're not cubing it. You would have 2.61, that's its units, feet cubed. Okay, but you just take that number, 2.61, times 12 to the third times 2.5 to the third. Okay, you have to do that so that your units will cancel. So basically you have feet cubed canceling here, and you have inches cubed canceling as well. Okay, and so our final answer when we multiply everything on the top and divide it by 1 should be about 7.39 times 10 to the 4th centimeters cubed. Okay, any questions on this one? Okay, use the same numbers that are on your conversion factor sheet. Okay, while you're looking at that one, if you have any questions, then go ahead and answer example 1-4. convert milligrams, 234 milligrams to kilograms. Everybody got an answer? Okay, what'd you all get? Okay. Okay. Same thing he got. She just put it in scientific notation, yeah. Okay, did everybody else get that? Okay. While I'm thinking about it, I just want to be sure and tell you guys that I do give partial credit for these problems. So even if you just set the problem up here like so, you write out what you know and put your units below. Hopefully you can go further than that, but even just for that, you can at least get a point or so. So the more work that you show, the better as far as how I grade. So if you just leave something blank, then, you know, that's a lot worse than at least trying. So, okay, so we have 1,000 milligrams in 1 gram. Okay, so you have to think about your plan. So I chose to go from milligrams to grams and then from grams to kilograms. Okay, there are obvious shortcuts that you can use, especially some of you are thinking, why don't you just divide by, I'm sure on other ones, just divide or just multiply. But there's a reason that I'm showing the units, showing how everything cancels out, because it does get more complicated as the semester goes on. So we want to start out right and writing everything out stepwise. Okay, and then we have 1,000 grams in 1 kilogram. Okay, so grams cancel. We're left with kilograms, not canceled out, which is what we want as our units. Okay, and so we end up getting 2.34 times 10 to the negative 4 kilograms. It's a pretty small number, so you probably would want to go ahead and put it in scientific notation. Yes. Yeah, it's just scientific notation. So when you plug this into your calculator, what did you get? Do what? Okay, you've got to divide. So you're basically going to be, you're dividing by 1,000 times 1,000. So you're going to end up moving your decimal 6 places. Okay, so it's going to be, it's divided by that, so you're going to have to move your decimal to the left 6 places, which then you can put in scientific notation. Okay, so from this point, you should be able to work the worksheet 1. Okay, we're going to go ahead and finish up chapter 1 real quick, and then if we have time, we'll work on those worksheets. But you hopefully have already started working on it, but if you haven't, you definitely want to start now. All right, we're going to talk about a term called density in lab as well as in class, but you're going to actually determine the density of an object in lab. Okay, and I'm actually going to kind of show you how you're going to do this in here. Density is the mass per unit volume of a sample of matter, so of an object of any kind. Okay, it's a characteristic property, it's a physical property of matter, and a lot of densities are tabulated for you, so we know the densities of lots of different chemicals and lots of different objects. Okay, it's the reason why ice floats in water. Ice is less dense than water, so whatever is less dense is going to be the top layer. Whatever is more dense is going to be the bottom layer. So you're going to see this as well in lab. So you may mix 2 chemicals together and shake them up in a test tube, and you may get 2 layers. Well, the top layer is going to be less dense than the bottom layer. Okay, the density of water is 1. That's pretty easy to remember. I think I may even tell you on the exam, but if you need density of water, it's 1 gram per milliliter. Okay, remember that density is mass per volume, so we have to have units of mass and volume. Okay. Another conversion factor that's also on your conversion factors list is that 1 milliliter is equal to 1 centimeter cubed. Okay, that's one that you do want to be sure that you remember. Okay, so we're going to look at how to calculate the density. Okay, density is equal to mass over volume. Okay, keep in mind, and really for the rest of the semester, when we have an equation, we can, here we're just going to plug in mass and volume. Okay, but we have 3 variables. Okay, we have to be given quantities for 2 of the 3 variables in order for us to solve for density. Okay, if you weren't given mass, and I just told you a volume, well, that's not really going to get you anywhere. Okay, you have to be given 2 of the 3 to solve. Okay, so we have a substance that is 742 grams, so that's its mass, and it occupies 97.3 centimeters cubed. Okay, this is where you have to remember that 1 centimeter cubed is equal to what? Equal to 1 milliliter, exactly. Okay, so you don't get confused if it is put into a problem. Okay, so basically we can write this out as centimeters cubed or milliliters. Okay, so then we just plug it in. So we have 742 grams. So density is equal to mass over volume. So grams is our mass, 742. And our milliliters, or centimeters cubed, is our volume. So then we would plug this number in the denominator, and we would find the density of this substance to be 7.63 grams per milliliter. Okay, don't forget to put your units as well. I will count off a small amount, but we'll count off for not putting the units. Okay, suppose you need 125 grams of a liquid for a reaction. What volume do you need if the density of this liquid is 1.32 grams per milliliter? Okay, I want you guys to think about this one for a minute. See what you come up with. Okay, we're given density, we're given a mass, and we're looking for volume. Yes, it would be. Okay, so we can rearrange the equation. So like I said earlier, when you're given an equation, we'll do this a lot, you can rearrange it. So depending on what you're trying to find. Okay, so we're looking for the volume. So if we rearrange, which is by this symbol here, okay, so hopefully you learned how to rearrange equations in your math class. But if you haven't, basically we can move things around so that we're now solving for volume, and it's equal to mass over density. So basically we swapped these two guys here. Okay, and now we can plug in for mass. So we have 125, and we have our density with units of grams per milliliter. Okay, notice how our units cancel. So here grams and grams can cancel. And we're left with milliliters, so 94.7. We use 3 significant digits because we're given 3 significant digits in the problem. Okay, and so that's how many we are going to use. Okay, we also have 3 here, so. Okay. In your book, it will often, especially in some of the word problems, it will ask or tell you that the specific gravity of a compound or a liquid is such and such. Okay, and so to prevent confusion, I usually use the term density because specific gravity seems kind of redundant, but I do want you to know what it means. So specific gravity is the density of the substance or the unknown or whatever you may be looking at over the density of water. Okay, well the density of water is what? More times than not at room temperature and is 1. Okay, so basically you're just dividing the density by 1. Okay, you end up with no units because your units of density cancel each other. Okay, so it would say in your book, it might say the specific gravity of hexane is 0.61. Okay, and it won't have any units there. Okay, well you will use it just like you would use density. Okay, so it's basically the same unless it says the density of water at some temperature, is not 1. Okay, but I'm not going to do that. So, but there is a difference. However, if it's given to you in a word problem or you see it in your book, it's used just like density. Okay. Did I skip something there? No. Okay. Okay, you guys are going to be doing volume displacement in lab today. So you're going to determine the volume of an object. I think it's aluminum and copper and iron are the 3 objects that you will go up and choose one, and you're going to determine the density of the object and then compare it to the actual known value or the actual known density of that object. Okay, so what you're going to do is you're going to submerge the solid down into water. Okay, and the volume, so if you see here, so we start at a certain level. So we have so many milliliters of water in a graduated cylinder. Okay, and then you add an object. It's not going to be a key. It's just the best picture I could find. I couldn't find one of our objects. Okay, and so you're going to submerge it. I'll go ahead and tell you to be careful with this because graduated cylinders are glass. Okay, and you're going to be dropping a metal down in there. Okay, it's got a string on it for a purpose so that you don't just chunk it down in there and break the bottom of the cylinder. Okay, it happens. Okay, you have a string on there so that you can lower it down slowly into the graduated cylinder. Okay, the volume is going to rise when you do that, and by the amount that the change in the volume, this is going to be the volume of that object. Okay, so here's kind of a problem, very similar to what you guys would do in lab. So if you have a 31-gram piece of chromium, and it's dropped into a graduated cylinder that contains 5 mils of water. Okay, so this would be your 5 mils of water. Okay, and you drop it down in there. So you drop down the chromium, and you know the mass. So you guys are all going to determine the mass of your object on a balance. Okay, and the water level rises to 9.32 mils. Okay, so you read your graduated cylinder, and you see that it goes up by that much. And then it asks, what's the specific gravity of chromium? The reason I use specific gravity is just to remind you again that basically specific gravity is what? Is density. Okay, so it's density without units. Okay, it's divided by 1. Okay, so I want you guys to find the specific gravity. So take a few minutes and see what you come up with. Okay, so it's easiest. First thing will be to do find density, and then we'll get rid of the units and divide by 1. So find density first. Okay, so the volume of the chromium in this case is the difference in the final and the initial. Okay, so your final volume is 9.32 and your initial is 5. So the difference in those two is going to be the volume of the object. Okay, so when we divide these two, we should get about 7.18 grams per milliliter. Okay, that's what everybody got? Okay, and if we're looking for specific gravity, so really it's just density without units, but we'll go ahead and show. We would divide the density by 1 because that's the density of water. Therefore, our units cancel, so we're left with 7.18. Do what now? It would tell you the specific gravity of this substance is 7.18. Okay, any questions?
So the volume of the substance is what the water level rises to times what it breathes.
Yep, here I'll show that. So here's your final volume. Okay, and this is your initial. Okay, so to get a difference in these two, you would take final minus initial volume. Not picking up my pen. So you would take 9.32 minus 5. Okay. We're going to discuss the different temperature scales. I'll start first by saying that heat and temperature are not the same thing. It's easy to get the two confused. I know before I knew this, or I'll probably even do it on accident now, but I'd go to my thermostat and say the heat's on 75. Okay, well, technically I should say that the temperature is at 75. Okay, the temperature is the way that we measure heat. Okay, heat is the form of energy. Okay, and so technically we are measuring by the temperature, we're measuring the intensity of the heat. Okay, and so we have three common scales. We have the Kelvin and Celsius and the Fahrenheit scale. So this is just showing the freezing point and the boiling point of water. Okay, and so in comparing these two, so the freezing point in Celsius is 0 versus 32 for Fahrenheit, 100 degrees for Celsius, and 212 for Fahrenheit. And then you can look at this difference here for Kelvin. Okay, and so I'm just going to show you the relationships between these two and put them into an equation that you guys will need to know. Okay, for Kelvin, Okay, this will be very important later. We won't use this a whole lot until more the end of the semester when we're dealing with gases, because all of our gas laws have to be in Kelvin. Okay, so we'll have to convert from Celsius to Kelvin. Okay, and how we do this is we take whatever that degree Celsius is and we add 273, okay, because that's our difference here. You see here we've got difference in 273. You look at a ratio between the Kelvin and Celsius scale. Okay, and then you can rearrange that equation. So say you were given Kelvin and you wanted to go to Celsius, then you could also rearrange and solve for that. But more times than not, we're going to be taking Celsius and converting to Kelvin. Okay, and so technically this number is 273.15. I can't remember, your book may use that. You're welcome to use 273.15, or you can remember just 273. Okay, this kind of shows the ratio. So if you look back at those thermometers there, for every 180 degrees in Fahrenheit, there's 100 degrees in Celsius, and so it just kind of shows you how we're just reducing a ratio until we get 5 divided into 9, which is 1.8. And so this number just didn't come out of thin air right here that converts from Celsius to Fahrenheit. You actually take 1.8 and you multiply it times the temperature in Celsius, so whatever that would be here. So this is kind of your variable. Okay, so maybe 25 degrees Celsius or whatever that might be. And then you add plus 32. Okay, so you will want to remember this one. Okay, and we can do the same thing. We can rearrange the equation. So if we isolate degrees C by itself and we rearrange, then we get degrees Fahrenheit minus 32 over 1.8. Okay, and so for both of these and for the Kelvin, if you have questions on rearranging equations, you could ask me after class, but both of those are just rearranging it to solve for a different variable. Okay, but the key thing that I really want to be sure you know, this one here, and then previously be this one. Okay, because if you know those, you can solve for the other. Okay, so we measure heat and in joules. Okay, that's the SI unit for heat is the joule. You can also use the calorie. I'll check and make sure, but I don't think I put anything on your exam about converting from calories to joules. But in every calorie, there's 4.184 joules. So I would give that to you, or it'd be on your conversion sheet. Okay, but once again, we actually start Chem 2 with this. Okay, so we talk a lot more about heat and energy in Chem 2, but I do like to at least introduce it to you, because a lot of you hopefully will move on to Chem 2 and it won't just be something brand new. Okay, so we cannot just measure heat alone. Okay, what we actually measure is the temperature, like I just said, so we can see the rise or the drop in the temperature. Okay, we can't just measure directly heat. Okay, Q is the symbol given for heat. Okay, you see it as uppercase and as lowercase, so don't let that confuse you. Okay, and our heat equation that we use is Q equals M times C. So this is an uppercase C. We'll talk about what it is in a second. Times the change of T. Okay, so M is mass in grams. Okay, C is specific heat. We'll discuss it. And delta T is the change in temperature. So it's exactly what we just did earlier when we took that final minus initial volume. We're going to do that for temperature. So you're going to take a final temperature minus the initial and see the change in the temperature. Okay. Specific heat, these are values that will be given to you. Okay, the specific heat of water is 4.18 joules per grams degrees C. Okay, it is kind of important to see these units here. And all it is the amount of heat that it takes to raise the temperature of 1 gram of a substance, so here would be water, okay, if we were finding the specific heat of water, by 1 degree C. Okay, and like I said, if I give you any other, even water, I'll give you the specific heat. So when you're plugging in for your C into this equation, this will be a known value. This will be something that I'll give you. And I give you the units, so you really don't have to memorize those either. Okay, so if we want to calculate the amount of heat it would take to raise the temperature of 200 grams of water from 10 degrees C to 55 degrees C. Okay, so when we're dealing with heat, you want to first just think of our heat equation, which is Q equals MC change of T. Okay, that's basically what you've got to know to solve this. Okay, Q is for heat. Okay, we usually, especially in Chem 2, this becomes really important when we're looking at chemical reactions. We want to see how much heat is released or absorbed by a chemical reaction. Okay, but for you guys, we're just looking at one substance. Okay, so we're just looking at water, and we're looking at how much heat it would take to raise 200 grams of water from 10 degrees to 55. Okay, so we plug in our mass. This is given to us, and technically here is how they sent this to me, but technically should have 200.0. So we should have exactly what is given to us in the problem. I don't know what's going on. We may be about to crash here in a second. Okay, and then we have to plug in for C. Okay. Okay, and this would also be given. So we would say, so somewhere in the problem you would have the specific heat of water is equal to 4.184. Sometimes you see it as 184 or 0.18 joules per gram per degree C. Okay, so we have mass 200.0 grams. And we have our specific heat 4.184. And then we have to multiply times change of temperature. Okay, so to get our change, we take the final minus the initial. So we take 55.0 minus 10.0, give us 45.0. Okay, and then we multiply out. So we take 200.0 times 4.184 times 45.0. Okay, and notice that we have to have the correct units here that match up with our specific heat. Okay, our mass has to be in grams so that our units can cancel. Okay, and then our degree C can also cancel. Okay, so we're left with joules as our units, which is the SI unit for heat. Okay, and so you want to be left with joules. You don't want to be left with joules per gram or anything like that. Okay, that's why you have to have grams in, or mass in grams, and temperature in degrees C. And so we end up with 3.76 times 10 to the 4th joule. And you can convert this to kilojoules if you want to. It's just dividing by 1,000. Okay, so pretty much the exact same problem, but now we're going to look at it with respect to mercury instead of water. Okay, so you guys calculate the amount of heat needed to raise the temperature of 200 grams of mercury. Okay, and the big difference here is that the specific heat of mercury is a lot different than that of water. So we take our mass, 200 grams, times C, so here's our C, our specific heat, times the change in temperature. Okay, so this problem and the previous problem are exactly the same, except for our specific heat is different because we're dealing with mercury versus water in the previous problem. Okay, so grams cancel, degrees C cancel, and we're left with joules. Okay, so if we were to write out 1.240, and if we want to look at this in kilojoules, all we would do is divide by 1,000. Okay, so now we're going to compare the two. So, like I said, the biggest difference is we have two different substances, and we've raised them. The temperature has changed by 45 degrees for both. Okay, but they have different specific heats. Okay, so that's the biggest difference here. Okay, so if we look back at our answer, so we got about 37.6 kilojoules for the water. That's how much heat we needed. And then we got 1.24 kilojoules for mercury. So a significant difference, right? So we needed a lot less heat for the mercury as we did for the water. So about 30.3 times more heat for water than for mercury. Okay, and this is because everything was the same except for the specific heat. Okay, therefore, if we look here, the specific heat of water is about 30.3 times greater than that of mercury. Okay, so that's our difference. That's what makes the difference in the amount of heat that was needed. Okay, so basically, point of all this, if we think about just a general idea, okay, the lower the specific heat value, say, so that term that's going to be given to you. So here, for mercury, it was a lot lower, 1.86 or 1.38. Okay, the lower the specific heat, the less heat it takes to heat the substance up, okay, and so it's going to be faster at heating. Okay, so if we look at mercury and water, which one's going to heat faster? Mercury, okay, obviously we see that it only takes 1.24 kilojoules of heat to heat up the mercury, okay, and so the mercury is going to be have a lower specific heat. So the lower the specific heat, the less heat it requires to heat that substance, and so the faster it is going to heat. Okay, so let me give you another example that I wrote down here. So if we have copper here, it's got a specific heat of 0.385, and we've got iron. So we have copper and we have iron of two different specific heats. Okay, so which one of these metals, copper or iron, do you think is going to heat faster? Okay, exactly. It's got the lower specific heat. Okay, you actually can get into this with people that deal with cookware. They look at the different metals and which ones heat faster. But then you run into an issue of, like for instance, copper. Heats fast, but it's not dishwasher safe, and there's all these other kind of pros and cons to cookware. But this is something that they have to think about. So exactly. So the lower the specific heat, the faster it's going to heat because it takes less heat to have to absorb in order to raise the temperature, okay, of that substance. Okay. Any questions on this? Okay. For the remainder of class, if you want, we ended up taking up more time than I thought, but you can work on, this is time for questions. I try to leave a little time at the end for questions, work on your worksheets. A reminder before you guys leave, tomorrow is the big symposium day. So, and the student success, for student success, there's an activity center that will be, they'll set up outside on campus where they will talk about different clubs, all that kind of thing. But the symposium is in the gym at 11 a.m., okay? And if you go and stay and get a voucher and bring that voucher to me, it's worth 5 points on your first exam, okay? So just why? Yes, I will see you guys at lab. Yes. It's just an hour. Yeah, it should be done by noon. Yep. All right, you guys have a good day. See some of you in lab.